So today we're going to do more improper integrals. So if you want a title for this, this is like Improper Integrals, the sequel. So the ones that we did last time, let me just flip this sheet over. We looked to positive or negative infinity. So we were looking at horizontal asymptotes. These were some pictures that we drew to go along with those. So again, we were looking at horizontal asymptotes. This time we're going to look at vertical asymptotes. So it is different, but not very much. So let's just draw some pictures of what these are going to look like. So the first one, because I think a visual helps. If a function is continuous on A to B, but notice there's not a bracket on B, and has an infinite discontinuity, that means a vertical asymptote at B, then, all right, this is what this would look like. You would have something like this, and that asymptote happens at B. And so the area you're finding is this. So again, instead of a horizontal asymptote, now you're looking at a vertical asymptote. But if you read through this, you kind of set it up the same way. Now they changed this to C. Again, like what's in a name? I don't really care about the letter. I'm going to continue using A for the lower boundary and B for the upper boundary just for consistency's sake. But you would approach this value from the left. And do you get why it's the left? Like the only side that you got. Okay. You would approach this value from the left, just put that limit out front, and then change that upper boundary to that new letter of the alphabet. Again, you're basically just moving the problem outside of the interval. Same thing if it's on the other side. If you're continuous from A to B, but not including A, so something like this, where you have, I didn't draw that one very well. Let me do a take two there. Where your vertical asymptote is at A, and then you're finding this area. So same thing, but you would approach A from the right. I'm going to put in the little from the left and from the right. I'm not super overly concerned about that. I mean, like, it's true. If you left it off, I would let that go. I mean, like, as long as you get the right answer, then it's fine. So those are pretty straightforward. This is actually the one that's kind of tricky. If you're continuous on A to B, except for a vertical asymptote that's somewhere in between. So that would be like if you had a vertical asymptote and you were trying to like find this area, you just have to be really, really, really paying attention to what you're doing, because if neither of the boundaries has the asymptote, you might miss it. And I have an example on here. We'll compare and contrast, like, hey, what happens if you mess that up? You won't get the right answers. You just have to be aware of what the graph looks like. And once again, if you get an answer, great. Otherwise, it diverges. All right, so let's try a few examples. Again, this isn't going to be super a whole lot different than last time, but I mean a little, because it's a vertical instead of a horizontal asymptote. So where is the vertical asymptote for this graph? Good. 0 is where you would have the 0 denominator. So that's why this is an improper integral, is because you have a vertical asymptote at 0, and 0 is one of the boundaries. I'm going to use A since it's the lower boundary, and we're going to approach 0 from the right. Because if you're going from 0 to 5, you would have to approach 0 from the positive side. So limit as A goes to 0 from the right, integral from A to 5. I'm going to write that as x to the negative 1/2 dx. It is the exact same thing you did last time. You set it up with the limit. Now we're going to do the antiderivative. It'll be upper boundary minus lower boundary, and then you evaluate the limit. So you go through it the exact same way. All right, so antiderivative, you have to add 1 to the power. So now it's positive 1/2. 2 goes out front, such that A to 5. And then one more time, you got to write the limit, upper boundary minus lower boundary. So if you plug in 5, To the 1/2 power would be square root. So that'd be 2 square root of 5 minus 2 square root of a. And lastly, you evaluate the limit. So as a goes to 0, this entire thing goes to 0. And so your answer is just 2 square root of 5. Again, I know we're not like super excited to be here at the end of the day right before Thanksgiving, but isn't that cool? You can find an area of something that goes to infinity. Like that is neat, okay? Now here's where my question would be if I was sitting where you are. Isn't this a P series? What is P for this? 1/2, and doesn't it diverge if it's a half? Remember, it's kind of reversed now because we're looking at vertical asymptotes instead of horizontal asymptotes. So remember that whole P series thing, that only worked if you're going to infinity. This was a limit going to 0. And so I made up an example for you to compare and contrast that. So here's a P series. It's the same problem. I just changed it to an x squared so that we could see how this works out side by side. So this is a P series. P is 2. So you would kind of think like, oh, 2 is bigger than 1. We're going to get an answer. But again, it's opposite because it's not going to infinity. It's going to 0. So this would be limit as a goes to 0 from the right, integral a to 5. This is x to the -2nd. And then what would that antiderivative be? Verbalize. That's okay. I'm not going to yank you in the hall and make you take a verbal exam like in language class. All right, -1 over x such that a to 5, and then it's upper boundary minus lower boundary. I'm going to go ahead and say this, and we'll talk about it next week too, because half of you, and I actually haven't finished grading them yet, so it might be almost all of you got this note written on your quiz. I didn't take off, but a lot of you skipped this step and just went straight to the answer. You need to write that on the AP exam. I didn't take off points, but you have to do the fundamental theorem of calculus. Upper boundary minus lower boundary. Because a lot of you just knew which part of it was going to go to 0, so you just went and wrote the answer. I gave you credit. Again, for them, you're going to have to write it. Okay. So this would be -1/5, and then minus -1 over a. Now, when you go to evaluate this, you're not going to infinity, you're going to 0. So look what happens here. Do you guys see what's going on there? You have a 0 denominator. That part is going to go to infinity. And so this diverges. So you just have to be careful about how they're different. And again, that's why I kind of typed this up for you. Like I have some of them on one side, some of them on the other. It's the horizontal asymptotes versus the vertical asymptotes. So if you think of the graph of one, these negatives cancel. If you think of the graph of 1 over a, that's your regular old rational graph. Are you guys following me here, like the hourglass one? As you approach 0, it goes up to infinity. I always fall back to a graphing approach because I'm a real visual person. I like to look at a picture. So I always just kind of think of what the graph looks like when I encounter something like that. I guess we'll do this one. Sorry, that's a cube root of x. So where does that graph have a vertical asymptote? 0. This time it's the upper boundary, so I'm going to use b, and we're going to approach from the left, because if you think of from a to b, you would be approaching from the left side. So limit as b goes to infinity. Oh no, I'm sorry. 0, thank you. I just like said that too. 0 from the left, integral from -1 to b, and then this would be x to the -1/3 dx. All right, so I'm going to rewrite the limit. Antiderivative, we're going to add 1 to the power. So that would be 2/3. So out front, we need 3/2, such that -1 to b. And then don't skip this step. Even if like you know how it's going to turn out, make sure you do the fundamental theorem of calculus. It's upper boundary minus lower boundary. So plugging in b, it's just going to be that, except with a b in it. And if you plug in -1, all right, this would be -1 squared, and then you're going to cube root that. What it means is this, to the 2/3. So -1 squared would just be 1, and then cube root of 1 is 1 times 3/2 is 3/2. Perfect. And then lastly, evaluate the limit. So as b goes to 0, this entire first part is going to be 0 minus 3/2, and so you get -3/2. That area, don't forget what you're finding. When it's an integral, it's area under the curve. That area is negative. So what does that tell us? Below the x-axis, below sea level. Does anyone else see 1 over x and then immediately think like what it's going to be, like ln, like, I don't know, I see that and I'm like, oh, ln. Yeah. All right, so the problem is 0. So it's going to be limit as b goes to 0 from the left, integral -2 to b 1 over x dx. That first step, you're kind of like not doing anything. You're just rewriting. You're setting it up with the limit in there. So rewrite the limit. Antiderivative will be ln such that -2 to b. And then don't skip this step. We're going to do upper boundary minus lower boundary. I just wrote it as ln of 2 because you're going to absolute value it anyway. And also it doesn't really matter because as you go to 0, and I know it says from the left, but you would absolute value that. As you go to 0, think about your ln graph. What's going on at 0? It's going to -infinity. So the whole thing doesn't matter anyway, it diverges. I just have a couple more and then we'll do a break, hang in there. And actually this one we won't even work out the whole way. I just want to illustrate for you sometimes what can like accidentally happen. Here is a common mistake that can happen. Is you can see that and go, oh, this antiderivative is ln of x such that -2 to 4. Do you see how this can accidentally happen? And then you would have ln of 4 minus ln of 2. Why is that wrong? There's an asymptote at 0. I'm not going to make us redo this problem because we know it's going to diverge. We just did this exact same problem, -2 to 0. It's going to diverge, but let's just set it up. You would have to do from -2 to 0 plus from 0 to 4. And when you work those out, again, I'm not going to make you do it again because we just did it right here. But when you work this out, you're going to get that it diverges. But you had better believe that if that was a multiple choice question, they would make this one of the wrong answers. Do you know what I'm saying? Like, so you just have to be really, really vigilant because sometimes the issue is not one of the boundaries, it's in between. You have to know it's there. Yeah, or like not close enough. And I'm going to be real honest with you. My brain isn't really big enough to totally understand that because a lot of times there will be a horizontal asymptote and it still won't diverge. It just has to do with the way the series of numbers works as it goes out to infinity. If it's not getting close enough or leveling off enough, then you won't get an answer. Yeah, same thing. And again, to be perfectly honest, I don't really understand because I know it levels off there and you're like, well, why does this one give us an answer and not that one? It has to do with like the way in which it gets closer. Because what did we do? One that had a square root and one that had a squared and one that was to the half. They're all just like mathematically slightly different. And all I can say is refer back to the limits that we did, and you can see why some of them work and some of them don't. Are you sure? Okay. What was I talking about? I was done with that one, right? Okay, I was just gonna do one more. So same thing for this one. You could very easily accidentally get the wrong answer. If you just did an antiderivative, upper boundary minus lower boundary, you have to notice that there's an infinite discontinuity in there. So where is there an issue? At 0. So you're gonna have to split this -3 to 0. I'm gonna write it as x to the -1/3, and then 0 to 1, x to -1/3. So pep talk. You're going to write a little bit for this one. Like it's going to be very repetitive because you're doing the same thing twice. We did one like this last time. Do you remember when we did the integral -infinity to positive infinity? And you have to break it somewhere in between, and we basically did the same problem twice. This is going to be the same kind of thing. So this first one, limit as b goes to 0 from the left, integral -3 to b of all of that, plus, and then this one would be limit as a goes to 0 from the right, integral from a to 1 of the exact same thing. So again, we're going to do a little bit of recopying here. You're going to all be okay. Like you'll survive. It's going to be totally fine. Anyone can write the same thing twice. All right, so what is our antiderivative for this? Two-thirds, good. It'll just be 3/2. Yep, 3/2 x to the 2/3, such that -3 to b. And then this one's going to be the same thing. It's more just like notation overload than anything. Like it just looks like a whole mess of symbols, but you're really just writing the same thing twice. So then it's upper boundary minus lower boundary. I hope I can fit this on here. Limit as b goes to 0 from the left, upper boundary minus lower boundary. So that's going to be 3/2 b to the 2/3. All right, if we plug in -3, so it would be -3 squared. That would be 9, and then cube root of that. So it would be 3/2 cube root of 9, whatever that is. And then this other part, limit as a goes to 0 from the right, upper boundary minus lower boundary. Barely made it. If you plug in 1 to this, you're just going to get 3/2. And if you plug in a, it's just going to be the same thing with an a in it. And then last, you're going to evaluate the limits. They all go to 0. Okay, so for this one, as b goes to 0, this part's gone. Minus 3/2 cube root of 9 plus, and then as a goes to 0, this part's going to be gone. So it would be 3/2 minus nothing. So again, it was really repetitive, but you do have to split it, because if you just did the antiderivative and then plugged in 1 and plugged in -3, it's not going to come out to the right answer. And same thing for this one. So you just got to be careful as well. So this is also sort of a sequel lesson. This is the fundamental theorem of calculus part 2. So I'm going to review the first part and then we'll look at the second part. So the first part is integral of a derivative, and it gives you area under a curve. So that is what it tells you. It gives you that area under the graph. And so it is integral from a to b, f prime of x dx. Which would give you f of x, integral and derivative cancel each other out. So you just have f of x from a to b, and you do upper boundary minus lower boundary. So that is your fundamental theorem of calculus. You take an antiderivative, upper boundary minus lower boundary. So if we reverse that, derivative of an integral, remember a derivative is a rate. So this is the rate at which the area is changing. And so what we're headed towards is accumulation and how quickly you accumulate area or how much area you are accumulating, which is also one of my favorite lessons. That's the lesson we're going to come back after Thanksgiving and do. So I'm glad that that's what we're coming back to. So there's really only one rule, but there's kind of three ways this can turn out. So I'm going to show you all three. D dx is instructions, which mean take a derivative with respect to x. So that's your instructions. Take a derivative with respect to x. A to B, and I'm going to use t for this, and you'll see why. That's f of t dt, because the x is going to go somewhere else. Now, if A and B are values, like if they are just numbers, you would do this antiderivative, you would do upper boundary minus lower boundary, and you would get a number. You would just get a value. What is the derivative of just a number? So this would be nothing. So if both of your boundaries are values, like they're not a variable, it will just be 0. Are you remembering this? Or? So the reason this has to be t inside of here is because the variable goes as one of the boundaries. So d dx, integral from a to x, f of t dt. The derivative and the integral undo each other, and you would just get f of x. This one just came out to 0 because those were both values. Now you actually have a variable in there. Essentially, though, you just take this x and plug it in. Like, that's really all that's happening, right? And then the last way it can kind of look is if it's more than just x, like if you have an actual, like x to the third or sine of x or square root of x, like if there's more than just x, then it's going to involve a chain rule. And so you would get f of g and then chain on the derivative of the guts of it, like chain on the derivative of that inside part. Essentially, you just take whatever's in this upper boundary, plug it in, and then do a chain rule. If the boundaries are reversed, what do you put out front? Negative. You negate the whole thing, okay? We're just going to try these. They go rapid fire because once you start to see like, oh, like I basically do nothing. For this first one, derivative with respect to x from 5 to x. All you're going to do is take x and plug it in. I'll tell you, the only way people mess these up is if they do something. Don't put a plus c, don't take a derivative, don't take an antiderivative. The derivative and the integral cancel each other out. It's just going to be x squared plus x minus 7. 4x. Thank you. Copy error. So don't do anything, but please do write the problem correctly. That's like the 9th time I've done that today, and I'm so sorry. I'm like at the end of my rope too. It's like a complete brain-hand disconnect. I apologize. Yeah, I just need to sleep. I'm on like no sleep. This is what it looks like on no sleep. All right, this one, you're just going to plug in x, but you have to negate the whole thing y. It's reversed, like it's on the lower boundary. So what I would do is just stick a negative out front, like draw some blank parentheses, and then you're just going to plug x in for t. So it would be x squared minus x. Distribute the negative sign. You would have negative x squared plus x. I usually get asked like what happened to the 3. 3 is a number. The derivative of a number is just 0, so it's nothing. All right, here you're going to plug in the 5x, so it would be e to the 5x, but this one involves a chain rule. You have to chain on the derivative of 5x, which would be 5, and I would just put it out front. So 5e to the 5x. I know, because you're used to doing an antiderivative, you have to switch gears in your head, it's tough. Here, you're just going to plug in x, so it would be sine of x, but because the boundaries are reversed, it will be negative sine of x. Why is this one 0? They're just numbers. Derivative of a value is 0. All right, here we're going to plug in x to the third. So it's cosine of x to the third. And then you have to chain on the derivative of x to the third, which I'm just going to go ahead and put out front. That would be 3x squared. All right, here, there's a chain rule, and we're going to have to negate the whole thing. So actually, let me take care of that stuff first. I'm going to put a negative out front. The derivative of x squared would be 2x. I just went ahead and wrote that first. It doesn't matter what order you put it in. And then you're going to take x squared and plug it in. So x squared squared be x to the fourth, and then plus 5x squared. And then distribute, that would be negative 2x to the fifth minus 10x to the third. So again, negative because the boundaries were reversed, and that 2x got multiplied on because there was a chain rule. We all still okay? All right, this one has a variable in both of the boundaries. So you're going to do upper boundary minus lower boundary. So if you plug in x plus 3 for t, that would look like that. It would be 2x plus 3 minus 5. So that's the upper boundary minus, and then the lower boundary, just plug in x, it would be 2x minus 5. As a heads up, a lot of stuff, I think almost all of it is going to cancel. When you distribute, this will be 2x plus 6 minus 5. And then distributing the negative will be negative 2x plus 5. And it all goes away except for what? Yeah, the 6. Everything else cancels out and you just get a value. These last two are written strangely, but they're not actually hard. You just have to like read through what and interpret basically what they're asking you to do. If a derivative is 2x plus 1, find f of 6 minus f of 4. You want to think fundamental theorem of calculus. If they ask you for f of 6 minus f of 4, your brain should go integral from 4 to 6. Like that's what this should make you think of. Like that's what that should trigger in your mind. F of 6 minus f of 4. It should be an integral from 4 to 6 of this derivative 2t plus 1 dt. So fundamental theorem of calculus, the first part, you're going to do an antiderivative, upper boundary minus lower boundary. So what would this antiderivative be? T squared plus t, good, such that 4 to 6. And then upper boundary minus lower boundary. So if you plug in 6, let's see, that'll be 36 plus 6, so 42. And then if you plug in 4, you're going to have 16 plus 4, so 20, so 22. This is the one we're going to put in the calculator because this just gets a little bit weird. If f of t equals that statement and g prime of t equals that statement, on the AP exam, they're going to do this to you. They are trying to overload you with information. They're trying to throw you off. Just go, oh, they gave me 2 things. What do they want from me? They want g of 7 minus g of 2. Okay, what does that trigger in your mind that we should write? Good, integral from 2 to 7. Because if you can like filter out all that noise, it's like, what do they want me to do? Okay, now that's g. So which one of these involves g? Yeah, g, and you want the derivative, the rate should be what goes inside the integral, okay? So what goes inside of there is this thing, 5 minus t times f of t dt. Now, before I can type that in the calculator, what is f of t? Yeah, see, that's what they do is like, you almost have to work backwards. Like, here's what they want. And it's like, okay, so I set that up. And then it's like, oh, well, I'm missing this f of t. Oh, that's why they gave me that information. You know, they're going to give you all the information up front before you even realize what you're supposed to do. So you kind of have to ignore all that noise and go, okay, what do they want me to do? And then you'd be like, oh, that's why I need that other stuff. All right, what am I going to type? How do I type this in? Math 9. It says int if you forget that it's 9. 2 to 7. If I'm remembering, I think this comes out to like a really large number. And I know it says t, but I'm typing x. Yeah, because there's a cubed in here, so I think this is quite large. Did I type all that right? Please double check me. I'm at the point where like I need someone looking after me. Oh, that's not that large. 1381.25. You could, well, let's talk about how you would have. I wasn't going to make you, but what would you do with all this? Yeah, you would distribute this all to each other, get this big long statement, do an antiderivative, upper boundary minus lower boundary. I wasn't trying to torture you.